So what is an inductor? An inductor is an electrical component in a circuit that's able to turn magnetic energy into electrical energy. So as we all know, moving charges create magnetic fields, which is the basis of how an inductor will work. Inductors allow current to flow through it since they're usually coiled wires or solenoids. So when moving charges go through inductors, a magnetic field is created, and that's where the magnetic energy is stored. So here we have a circuit in which the inductor is in parallel with the light bulb, which is going to be our resistor. So when the circuit is first closed, the inductor has very high resistance, which means very little current can flow through it. However, over time, the longer the circuit is closed, the resistance will continue to decrease, and more current will be able to flow through it. And as we know, as current increases, the magnetic field around the inductor will also increase as well. And this will continue until both reaches the maximum. So as we can see with the graph, the current will continue to increase until it flatlines. So the second circuit is when it has been closed for a long period of time, and when the magnetic field is at the maximum, and there's the maximum magnetic energy stored. So in this case, since we know that moving charges like to take the path of least resistance, there will no longer be any current flowing through the light bulb. And this whole process is analogous to the water wheel, and how as the water continues to push against the wheel gets faster and faster until it reaches the speed of the water. So now we disconnected the battery from the circuit, and the only loop that remains is between the inductor and the light bulb. And so what will happen here is that the magnetic field from the inductor will push charges through the light bulb, and that's basically what it means when magnetic energy is turned into electrical energy. The energy stored in the magnetic field of the inductor is used up, and the field will decrease in magnitude. And what this shows is that inductors tend to resist changes in current. When we disconnected the circuit, the current decreased. So the inductor tried to stop that by pushing the charges through the light bulb, and thus maintaining the current through it. In addition, when the circuit is initially closed and current starts flowing through the inductor, a magnetic field is created which provides a sort of backwards EMF, and this is also an example of it trying to resist the changes in current.
So, what's a transformer? A transformer is an electrical component that is able to change the input voltage going through the circuit into the desired output voltage. It's called a transformer because it switches electrical energy into magnetic energy, then back to electrical energy. A transformer consists of two coils of wire, a primary coil and a secondary coil. These are wrapped around a bar of some sort. Transformers only work in AC circuits because transformers need an alternating current to create a changing magnetic field. How does it work? First, current passes through the primary coil, which creates a magnetic field that overlaps onto the second coil, which gets an induced current due to this field. This induced current only appears when there is a change in the magnetic field. If the field is static, then there won't be an induced current. The voltage change depends on the ratio of the number of turns of the primary coil and the secondary coil. For example, if 240 volts go into the primary coil with 10 turns, and the secondary coil has 5 turns, the output voltage would be 120 volts. Cores are what the coils are wrapped around to contain the magnetic field produced by the primary coil and guide it towards the secondary coil. That way, there will be maximum magnetic flux. Taps are places where the wire on the secondary coil sticks out, then goes back in. Taps allow a transformer to have multiple sets of turns to use to change the output voltage. What do transformers have to do with inductance? A transformer is made of at least two inductors, and inductance affects the induced current. For example, if the primary coil's inductance is less than the secondary coil's inductance, then the secondary coil's induced current is less than the primary coil's current, and the voltage goes up. And why is that? Since the power must stay the same, if the voltage increases, then the current must decrease.
The national grid is a very complicated and important system of the modern era. It is mainly broken up into two parts. One is electricity production, and the second is electricity transportation. Electricity is produced in a variety of different ways, but the most common is through gas turbines. This is when a certain fuel source like coal, natural gas, or radioactive particles are used to steam water. That high pressurized steam water is then aimed at a gas turbine where it rotates the turbine. The turbine is connected to a rod which is connected to a generator. That generator consists of a giant magnet surrounded by coils of copper wires and uses a very simple rule of electromagnetism where moving magnets can produce current. In this way, mechanical energy is converted into electrical energy. Within the second part, the electricity is transported from the producer to the consumer, but the process can be plagued with inefficiencies that are very much avoided through smart engineering. First of all, high current can give off a lot of heat when transported through power lines, which can severely decrease the efficiency. So engineers use transformers that convert the high current produced in power plants to high voltage, which can be easily transported. However, consumers cannot use that high voltage, so transformers are used again to turn the high voltage into usable current. That is the entire grid system.